Yes, sir.
All right. So
This call
last time
is now being recorded.
last time we
This call is now taking notes.
began to talk about reflection of light, and then we talked about reflection of light on plane mirrors, and then we said some few things about that, some few characteristics of images that are formed on plane mirrors. And I remember saying that the images, some of the characteristics or properties of images formed on plane mirrors is that the images usually are the same size. They have the same size with the object. They are the same distance. The distance from the screen to the image is equal to the object distance to the screen of the mirror. So we talked about that, and then we mentioned other few things also, that such as that the mirror images formed on plane mirror, we have lateral inversion. And I explain lateral inversion to mean that you standing before a mirror is as though your body flips side. So your left becomes your right and right becomes your left, and then stuff like that. So, and just few properties like that. And then we also talked about the curved mirrors, and I said we have two types of curved mirrors. We talked about the concave mirror
Con,
and the
con,
convex, right? Convex. But we didn't really talk about convex, I think, because majorly in convex mirror, the nature of the image is the same for every position. For every object position, it has the same nature of image formed. All right. So where we have little bits of issue, which of course shouldn't be an issue, is the concave mirror. And we really took time to explain the position of every image based on the object location. And I remember mentioning locations like if the object is at a distance, if the object is placed in front of the focal point, if the object is placed at the focal point, if the object is placed behind the focal point, if the object is placed at the center of curvature, if the object is placed behind the center of curvature, and then if the object is at infinity. So we looked at where will the images be formed for these various positions. And then, of course, we saw that in concave mirror, every time real images are always produced, except when the object is placed in front of the focal point. So if the object is in front of the focal point, we have a virtual image that is looking magnified, and then of course formed behind the mirror. All right, standing erect or upright. So these are the few things we looked at. So the convex, as I said, I'll just try to use a diagram to just explain that, because there's nothing really much for the convex lens, given that in convex lens, the object position or the image position is always the same, irrespective of where the object lies. So remember, let me try to sketch a convex lens here. So if I have, remember in convex lens, we have the silver coated area to be the inward side, which is the reason why it is called a divergent lens. So this side I'm putting this line are the silver coated area. So the other side, the side that curved outward, is the reflecting surface. All right. So if I draw my line, which actually is called the principal axis. I told us that this point here is a pole. Then the line that runs through the pole is called the principal axis. The principal axis is actually where every object is being situated. All right. So if I'll assume an object standing here, so let's say I have an object here. Last time I used a clear visual diagram to show this. I didn't do sketching. I was just explaining with an already shown diagram. So this is an object. If the rays of light comes from this object, it hits at this point, it is going to diverge. Because of the nature of this mirror, it is going to what? Diverge. So the light diverges like this. Meanwhile, the light ray came like this. All right. Also, I can consider another ray that traveled through this point like this. So let's say another ray travels through this point and also reflects along that same trajectory. All right. So the line through which the incident comes happens to be the same line in which reflection occurs. So if I assume that, so the light comes this way and then reflects back in the same direction. All right. So let's use this two rays to illustrate where the image will be formed. Now, of course, given that this line is diverging, of course, you should know that for the line to diverge, it means that a convex mirror can be referred to as a diverging mirror. Diverging mirror in the sense that if rays of light strikes on it, it will spread out. It's going to spread out. But for the concave mirror, if the rays of light strikes on it, it will converge. So we call the converging mirror to be we call the concave mirror the converging mirror. And of course, we call the convex to be the diverging mirror. So if I try to trace, these two lines can never meet on this side. This line will keep on going upward. This one will keep on going on its own direction. So these two ray line can never meet. So I can now try to trace a point behind the mirror where the image can be formed. And of course, if I extend this line straight, let me try to make it better. So let's say I keep my hand straight and extend the line downward. And also maintain this line like this, such that there'll be an intersection. My diagram may not really look so perfect, but I really hope you understand what I'm trying to say, all right? Or you just understand the picture I'm trying to create. Let me try to make it a little bit better. The line goes this way, and then this one continues to travel straight like this, something like that. All right. So if you use your ruler to sketch a diagram, you get a better picture. This point of intersection between these two rays behind the mirror will be the point where the image of this object will be formed. So the object will be formed like this. It will be formed standing erect, just like the original image, the original object. The only difference would be that it will now look small, it will look diminished. All right. And this happens to be the position of every image that is formed in a convex mirror, irrespective of the object distance, irrespective of where the object is kept in front of the mirror. All right. Every image that is formed in a diverging mirror, which is called a convex mirror, is usually formed behind the mirror. It is a virtual image because it can be caught on a screen. It always stands erect, just like the original object, and then it's looking smaller or diminished. So it doesn't matter the position where the object is. It doesn't matter the position, the distance. Sometimes you can see a question like this. WAEC or NECO might want to twist their question a little. They will tell you an object is kept 12 meters or 12 centimeters away from a convex mirror. Now they will not tell you, sketch using a diagram, an accurate diagram, show the position of the image formed by that very mirror. So you can't, whether they tell you 12 meters, 10 meters, or whatsoever meters, it doesn't matter where the distance of the object from the distance of the image from the mirror lies. The object will be formed behind the mirror, looking smaller, erect, and then is going to be, of course, a virtual image. And that is that for the diverging mirror, otherwise called the convex mirror. Now, what are then the advantages or the uses of these mirrors we've talked about? We began to talk about the concave mirror, and then uses of concave mirror. Let me just say uses of curved mirrors. I'll just talk about them generally. Uses of curved mirrors. So we begin with the concave. Basically, one of the basic or primary use of a concave mirror is that it's being used as a shaving mirror. That's the basic application, the one that usually is easier for you to recall. So the concave mirror is being used as a shaving mirror. Remember, the light that falls on the concave mirror converges. So as a result, it helps you, you can actually get a picture or a more image of what you are trying to do with your face. So if you look at yourself on a curved mirror, on a concave mirror, you can easily reach out to layers where the plane mirror might not be able to see, especially when you are trying to shave yourself, trying to do the whole of those cleanups, especially for the guys that has beards. All right. So the concave mirror is best used as a shaving mirror. It can equally be used as a dental mirror. That is to say, people, dentists, doctors, and that's the dentists, which are the doctors in charge of your teeth, they can use it as also as a dental mirror, so they can easily see into your mouth to know areas where they need to where there is a decay and the rest of that. So if a dentist wants to look into your mouth using the head of a mirror, so usually if any of you have had issue with your teeth and then you enter into the machine that is being used to maybe to check you where you do the whole of those stuff, you find out that the mirror that is attached to that machine is looking somewhat curved. It's curved a little bit inward. It's not looking very plain. If you look at it on face value, you might think it's a plain mirror, but actually it's actually a curved mirror. So it is being used as dental mirror. It can also be used as a shaving mirror. But for the convex mirror, the primary application or the primary use of a convex mirror is in the rear side view mirror of your car, of a car. So given that the convex mirror can see wide, can cover wide range, remember, is a diverging mirror. So light that strikes on it spreads out. So it can actually see things that are in a wider range. So it's being used on cars, is being used in the rear side view mirror of a car, of cars. Those two mirrors that are on the side is usually made of convex mirrors. Now, if you notice that usually there is an inscription written on those mirrors, they will tell you that objects in this mirror appear closer than they appear, are closer than they appear, something like that. So the objects in the mirror are closer than they appear. So the reason is because the image that will be formed will be looking diminished, is looking small. And then if you try to judge with your normal mental view to say that, okay, if an object is looking smaller, it means that the object is very far from your eyes. Now, if you try to observe something and it's looking small, it means that that thing is still very far, because the closer you get to the object, the bigger it is, right? But in a convex mirror, it doesn't appear that way. The object is bigger, but in the mirror, it appears small. Do you understand that? So it is being used in side view mirrors of cars, so that it can help you to see widely, and then you know how to navigate your way when you travel. So that is that for use of mirrors. I just wanted us to have that knowledge. Okay, so I want us to just look at calculations, how we can see questions involving calculations on this topic. So we've done the theories. I just wrapped up the little things I didn't say the last time. And now I want us to see the calculations as it applies to us, even in this topic. All right. But before we start the calculation, I want us to take note of something. Or let me just go straight and write the mirror equation. The mirror equation. The mirror equation. Now, this mirror equation is just an equation that shows us the relationship between the object distance, the image distance, and the focal length of a curved mirror. So anytime you hear about the mirror equation, just have it in mind. It is an equation that shows us the relationship between the object distance, the image distance, and the focal length of a curved mirror. And the equation says that 1 all over f, the inverse of the focal length, is equal to 1 all over u, which is the inverse, exactly, plus 1 over v, right? Correct. So where u is the object distance, and then v is the what? Image distance. All right. So u is the object distance, v is the image distance, and f is our focal length. So this is the mirror equation. Now, sometimes you might not be given F, but you'll be given the radius of curvature. Remember, the radius of curvature is the distance from the screen to the what? Center of curvature. So if you are being given the radius of curvature, have it in mind that F can be obtained by dividing the radius of curvature by 2. So if you divide the radius of curvature by 2, you get the focal length, right? Okay. So now, there are a few things I want us to take note as regarding sign conventions when we are dealing with this mirror formula. Because if you don't have the idea of when to use plus and minus, even though you know what you're doing, you might end up getting wrong results. Now, have it in mind, there are two ways of doing this, but I'll just tell you one and we stick to it. So no need to bring in two comparisons, just one, let's stick to it. And that is under the real is positive convention. Now, the first thing to note is that visual images are at a negative distance from the mirror. So anytime the image formed is visual, anytime it's not a real image, just know that the image distance must be negative. Remember, it means that convex mirror, if it's a convex mirror, the image formed in a convex mirror will always have a negative distance because a convex mirror can never produce a real image. Don't forget that. It only produces visual image. But a concave mirror can be positive or negative depending on the position of the object. Now remember, if the object, the only time a concave mirror produces a visual image is that the object will be kept in front of the focal length. If the object is kept in front of the focal length, the image that will be produced will be magnified and visual. It will be a visual image. It will not be a real image. It will be looking magnified and also be what? Visual. So visual images are at always a negative distance from the mirror. So don't forget that. So it means that real images are always considered to be what? To be at positive distance. So visual images are considered to be what? At negative distance. Real images are positive distance. Also, in fact, objects, real object distance and image and the real image distance are always positive. But if the distance is that of a virtual image, then it's going to have a negative distance. Don't forget that. And also take note that the focal length of a concave mirror is positive, while the focal length of a convex mirror is negative. Take note of that. I say that again. The focal length of a concave mirror is positive, while the focal length of a convex mirror is negative. So these are the things to note. Real image distance is positive, visual image distance negative, object distance always positive, focal length of a concave mirror positive, focal length of a convex mirror negative. So take note of this. It will help us solve problems as we move forward. All right. So having known that, I wouldn't forget the magnification formula, because many a times you might see they will ask you to find something on magnification. All right. So we can actually calculate magnification of an object. Magnification means how much the image produced is being increased. Remember, if you check the properties based on what we did in the last class, at some point I told you some image will be what? Magnified. So I want to know by how much did the image increase as compared to the original size. So that is what the magnification is all about. And you can calculate magnification by using this formula that magnification, capital letter M, is equal to the image distance divided by the object distance, U. So remember, image distance is V, object distance is U, all right? So the ratio of the image distance to the object distance will give us the magnification of that very object. Don't forget that. Also, if you were given the height of the image and the height of the object, so we can also say that magnification is height of object. So let me write it as H object divided by the what? The height of image. No, please. I think that's a mistake. Height of image, not object, please. Height of image height of image divided by the height of object. So take note of that. These are the formulas for magnification. It's either we use the image distance over object distance, or we use the what height of the image divided by the height of the object. And that is that for that. So these are the things we need to navigate problems on this very topic. So let's go straight in solving problems. Question, let's take an example. Question number 1. All right, so you will just take down the question while I just I'll call it out, and then you take down the question. The question. So the question says, an object is placed 15 cm in front of a convex mirror. So an object is placed 15 cm in front of a convex mirror, and an image is produced 5 cm behind the mirror. Don't forget, and an image is produced 5 cm behind the mirror. Now the question is, calculate the focal length of the mirror. Calculate the focal length of the mirror. So this is the question. So they gave us the object distance in front from the convex mirror, and they also gave us the image distance, and they want us to find the focal length. So it's a very simple one. All we need to do is just to apply the sign convention, and that's all. All right. So let's quickly work out the problem solution. Based on what the question says that the object is placed 15 cm in front of a convex mirror. Don't forget the mirror is convex, and the focal length of convex mirror must always be negative. And since a convex mirror produces only virtual images, it means that the image distance must also be what? Negative. Those are just the things to note, nothing else, nothing else. All right. So we were given that the image distance U is actually given as what? 15 cm from the question.
Yeah.
All right. And then the object distance V, this is object distance 15 cm, then image distance. I repeat, please. We were given that the object distance, which is U, is 15 cm. Don't forget that U is object distance. And then the image distance, which is V, is what? 5 cm. But if you work with this 5 cm like this, you are going to be wrong, because since it's a convex mirror, the image distance must always be what? Negative. Why? Because the image produced is not real, it's virtual. So I add a negative sign to that value there. All right. So having done that, we want to find the focal length. So we are looking for the focal length. We don't know what the focal length is. So I can put a question mark there. Then if I apply the formula, I'm going to have that 1 all over F equals 1 all over U, which is, let me write it out, 1 all over V. So this is 1 all over U is 15, 1 over 15 plus then 1 all over minus 5. All right. So this becomes 1 all over 15 minus 1 all over 5. So if I apply LCM there, the LCM for 15 and 5 is going to be 15. 15 divided 15 is 1, and 1 times 1 is also 1. 15 divided by 5 is 3, and 3 times 1 will give me 3. So this becomes that 1 all of 1 minus 3 will give me minus 2 over 15. Minus 2 all over 15. And that is my 1 all over F. Remember, everything I'm solving is 1 all over f, because 1 over f is what we are solving for. And from here, we can now find the f. If I cross multiply, I'll be having that minus 2f is equals to what? 15. All right. By cross multiplying, this times this and this times this. So if I divide both sides by minus 2, my f becomes 15 divided by minus 2. And then, of course, that will give us negative 7.5, which is correct because the focal length of a convex mirror is always negative. You see that? So the focal length is always negative, and this becomes the result of our answer, negative 7.5. So that's a very simple one. So let's proceed to the next question. Meanwhile, I don't know, is there any question at all based on what we just did now? Is it understood? See, nobody's responding. Always our issue.
That is, I understood.
Okay. Okay. It's very simple anyway. I wasn't expecting so much questions. I just asked. Okay, so let's look at similar problem or similar question. Now, this one says, let's call that example 2. In example 2, the question says we should calculate the position and nature, calculate the position and nature, calculates the position nature and magnification of an image produced if the objects is 15 cm in front of a concave mirror with radius of curvature with radius of curvature 12 cm. That's the question. So the question says that we should calculate the position, the nature, and magnification of an image produced if the object is 15 cm in front of a concave mirror with radius of curvature 12 cm. So when they say position, they want to know where the image, what will be the distance, at what distance will that image be formed? That's the question they're asking us, and that is what they mean by position. So when they said nature, they want us to tell, is the image formed, is it real or virtual image? And then when they say magnification, of course, you know what magnification is. You can always use the ratio of the image distance to the object distance to get your magnification. So let's start by calculating for the position of that image. Solution. So now from the what was given to us, we were given that the object is 15 cm in front. So given So we're given that our object distance U is 15 cm. And then they also gave us the radius of curvature R is 12 cm. So if R is 12 cm, it implies that our F is going to be what? 12 all over 2, which is 6 cm. All right. And then we're asked to find what else? We're asked to find the position. Okay, the position measurement. All right. So let's start by calculating for V, which is the image position. So let's put a question mark there. Now, remember, the way to solve this is using the mirror equation. So we can say that, recall that 1 all over F is equal to 1 all over U plus 1 all over V. But it is V I'm looking for. So if I make V subject, I can easily make V subject, and my V will be that I can have that 1 all over V. 1 all over V is equal to 1 all over F minus 1 all over U. Then if I put in my parameter, now somebody will say, okay, why didn't you put, you didn't change sign for what is given to us right here? The focal length, remember the focal length of a concave mirror is always positive. That's why I didn't put negative sign there. If this same question is being asked for a convex mirror, the F is going to be negative because F for convex mirror is always negative. So if I put in the parameters, the values into the formula, I have that 1 all over F, where F is given as 6, minus 1 all over U, where U is given as 15. So 1 all over 15. Everything is equal to 1 all over V. Now the question is, how then do I find the LCM of 6 and 15? Their LCM is going to be 30. Yes, 30 divided by 6 is going to give me 5. And then 5 multiplied by 1 will also give me 5. Put my negative sign. 30 divided by 15 will give me 2. And 2 times 1 will also give me what? 2. So that I'll be having that 5 minus 2 will become 3 all over 30. And that is my 1 over V. Remember, for us to get V, I can write it out that 1 over V is equals to 3 all over 30. Of course, if 1 over V is 3 all over 30, we can calculate V. We can now say, therefore, our V becomes the inverse, which is 30 all over 3. And 30 over 3 will give us 10 cm. You can see that that image distance is what? Positive. So the position is that the image will be formed 10 cm, whatever the distance from the screen is. So the image position is actually 10 cm from the screen. That's what we'll have there. Now, the next question we're being asked to find whether the image formed is real or not real. That's what they meant by what? The nature. And given that the image distance is positive, clearly it is a real image. The image formed is a real image. So if this, you can just answer the question by saying, since image distance is positive, it means that the image formed is real. All right. Now that is that for that. And then the next question we are being asked is that we should find the magnification. We should find the magnification. Magnification. How do we find magnification? As I said, magnification is simply 1 all over M, magnification M is equal to 1 all over, no, please, is equal to the ratio of the image distance to the what? Object distance. And what is our image distance right there? We're given that image distance from what we calculated is 10. And object distance was also given to us as 10. So 10 over 10 is equal to what? 1. 1 means that there was no magnification at all. So the magnification is still the same. The image formed is at the same distance as the what? Object. So this means that there was no magnification at all. And if I'm being asked, at what point will the image, was that image being placed? Something like that. So they want to know where exactly was the object placed to form an image that has the same distance as the object. That very object was placed at a distance at the center of curvature. So it is only when object is placed at the center of curvature that the image formed has the same size, and the same distance from from each object distance. What I'm saying is that if an object is being placed at the center of curvature, the image formed will also be formed at the center of curvature, and the size of the image will be equal to the size of the object. So it means that in this question, the object was placed at the center of curvature for that concave mirror, which is why a real image was produced, because the image form will be looking inverted, all right, the same size, and then will be formed at the same distance as the object distance. So that is exactly what this question entails, and that is exactly what we did is what the question expects us to do. All right, so we take one more question, maybe on this, and then we try to see if we can look at a little of just explain little things on refraction. Even though I know we won't have time to explain that, but I encourage you, as long as I don't think I was thinking the last class we had was actually our last class. I didn't know we'll be having a class today being Friday. So it means that what we are doing today is also to be a plus, but as much as you can, try to look at refraction. That's another area you should expect questions. And many a times, the way the questions comes, especially when it has to do with prisms, triangular prism per se, it might look a little bit dicey, but it is actually very, very simple if you understand how to do it. So I encourage you, try to look out materials, check out how to navigate problems that involves refraction, especially the ones that has to do with triangular prisms. If WAEC or NECO wants to set questions from refraction on prisms, they will always ask you about that of triangular. Most likely, you'll see questions on triangular prisms. All right. So, moving on. This one says that a concave mirror example 3, let me call it example 3. Example 3 says a concave mirror of radius of curvature 20 cm. A concave mirror of radius of curvature produces an inverted image inverted 5 times the size of the object. 5 times the size to stop. Now the question is, we should calculate the position of the objects and the image. They said we should calculate the position of the objects or image. And image, please, not an or. And image. Now there's another question added there. Is the image magnified or diminished? Is the image magnified or diminished? Okay, so this is the question that was being asked. So firstly, they said that a concave mirror of radius of curvature 20 cm produces an inverted image 5 times the size of the object. They said we should calculate the position of the object and image. And they also asked us, is the image magnified or diminished? So firstly, we need to start by calculating. In fact, when we understand the position of these images, we can now know whether they are diminished or actually magnified. All right. I don't know why they added that question right anyway. So solution. Now given, they say that a concave mirror has a radius of curvature. So we're given that, so we can say that our R is 20 cm. All right. So if the R is 20 cm, clearly it means that our F is R over 2. Remember. So we can say that it implies that our F is actually 20 all over 2, which is 10 cm. So that's the first thing. And now we were not given any other thing except that they gave us magnification. I think that last image there, they already told us that the image is 5 times. So why then are they asking us if the image is magnified or diminished? That's just a way to cause confusion in your head. The image is already magnified because they said the image produced is 5 times the original object. So don't even, just know that since the image is 5 times the original object, that last question there, the image is magnified. That's it. Okay, but we're not given another thing except magnification. So we can say that we're given that magnification M is 5. The magnification M is 5. So from here, we can do a little of, I think this will take us, we'll have to do a little of maybe substitution here. Recall that since we know F, we can say that 1 all over F is 1 all over U plus 1 all over V. But we are not given V and U, but we know that our magnification, M is actually equals to V all over U. So it means that we can say that 5, which is magnification, so it implies that 5 is equals to V all over U. So I have to just make substitution and plug it into the original equation. That's exactly what I'll do. See that I make V or U subject. So whichever one I choose to do, I am also correct. So, but clearly, if I cross multiply from here, I can see that it implies that V is equals to 5U. All right. So V is 5U from that equation if I cross multiply. So V times 1 is V and U times 5 is 5U. So I can now replace anywhere I see V in that mirror formula, I'm going to put 5U there so that all my equations will just be in terms of U. So this implies going back to the formula or put V equals 5 over U into the mirror formula, the mirror equation. We can say that it implies that 1 all over F is equal to 1 all over U plus 1 all over what? V, which is now what? 5U. So from here, what I'm going to do is to find the LCM. The LCM of U and U, the LCM of U and 5U is going to be 5U. 5U cancel U, I have 5 left, and 5 times 1 is going to give me 5. And then 5U cancel 5U, I have 1. 1 times 1 is going to give me 1. So I have that 1 all over F is equal to 5 plus 1 over 5U, which is actually 6 all over 5U. That's exactly what I'm going to have right there. 6 all over 5u. But we are given f. We know the value of f, all right? So let me go to the next slide. Remember from what we did, we said that f, since the radius of curvature is 20, our f, we calculated it to be what? 10. So, but f is equal to what? 10 cm. So it implies that I can have that 1 all over 10 is equal, from what we did now, to 6 all over 5u. So it's equal to 6 all over what? 5u. So if I cross multiply once again, I have that my 5u is going to be equal to what? 60. And then if I divide, my u becomes 60 all over 5. And 60 all over 5 is nothing but 12. So I've gotten the object distance. So our object distance is u, which we obtain to be what? 12 cm. All right. So having obtained the object distance, the next thing I'm going to do is to calculate the image distance. And this is very simple, just to put the value of u into the equation. Recall that we said that v is equals to what? 5u, from what we just did now, 5u. From this equation, look at it from here. From this equation, I put in a box that v is 5u. So I'm going to then substitute and put back my u into the v. I have that. It therefore implies that my v becomes 5 times 12. And if my v is 5 times 12, I'm going to be having that our v is what? 60 centimeters. So while the image distance is 12 cm, the object distance is simply what? 60 cm. All right, so I've been able to calculate the image distance and the object distance. So the next question they ask us there is whether the image is actually real, is magnified or diminished. And clearly, I already said, provided that the magnification there has already been mentioned as 5 times, they told us that the image is 5 times the object. So no need, you don't need to do anything. Have it in mind that that image was actually being magnified. So that is the solution to this very question. So that is that for that. Any question? Do we have any question? Okay, no one is saying anything. So I'll assume that to mean that no one has any question, since everyone is keeping calm. And our time is fast spent. We have barely 2 minutes. You see, the class we started late. We began this class. This class was scheduled by 9:15, 8:15. We started the class by 8:25. And I have an appointment I must start up with by exactly 9:20. So I may not be able to take us down to other things I would have want to do, but I will just maybe throw a little light on the refractions. Remember, we've talked about properties of light and properties of wave, and we mentioned reflection, refraction, diffraction, polarization, and interference. So what is this refraction? Refraction is simply the bending away of light anytime it crosses boundary of different density. So what does that mean? If light is traveling from air to glass, so because the refractive index of glass is different for the refractive index of air, the light will change direction. That change in direction is what we call refraction. The bending of light ray, if it crosses boundary between media of different densities, is what we call refraction. Don't forget that. And there are a few things, just like we have the law of reflection, we also have law of refraction, all right? And the law of reflection, the first law and the law of refraction is also similar. Just like we said in law of reflection, the incident ray, the reflected ray, and the normal ray at the point of incidence all lie in the same plane. So that also applies to the word refraction, all right? That applies also to the what? to the law of refraction. The first law of refraction is that the ratio, the incident ray, the refracted ray, and the normal ray at the point of incidence, all of them lie on the same plane. All right. And we have the second one, which is actually the basis for most of the calculations you do on this very topic, which is the Snell's law. Now, what does the Snell's law state? It says that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to a constant known as refractive index. That is it. So that is what the law is saying, that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to a constant for a given pair of media, and that constant there is called refractive index. So you have to try to see how to engage the Snell's law in solving problems on refraction. And also you should understand the concept of real and apparent depth. All right. So sometimes they will want to give you some little questions like this, just to test your idea of understanding on optical illusion, stuff like that. So you see, maybe you might be given a question that the depth of a swimming pool is this. When you're being looking, when you looked at it from the top, they want you to find, okay, what is the real depth? And then they'll give you refractive index. All right. So you should know that if you are being given the real depth, if you try to compare if you try to make comparison between the real and apparent depth, that ratio is called refractive index also. So you can calculate the refractive index of water if you know the real depth and the apparent depth. So that's what I'm trying to say. So if they give you the real depth, you can find the apparent depth by making it subject, because it's either they ask you to find the real depth or apparent depth, because the refractive index of this material will always be given. That of water is about 1.33, something 1.333, and then that should be around 4/3. And that of glass should be around 1.52. And then of course, the refractive index of air is approximately 1. And that is it for that. So, and many other things you have to just try to read it. So I'll just allow us, because I'll be leaving right now. I don't know if we have a question. And if you don't have any, I wish you guys success in your exams on Monday. Because just like I said, on Monday, every one of you, by the time it is this time, everyone is already done writing their physics exam. So thank you everyone for joining. See you guys in the next class. Bye.